Let's see, why would you choose the Suzuki reaction or the Heck reaction over each other? Slightly different substrate scope. So check out the Suzuki reaction. You can use, let's see, we got to do something about that, which is also in the way. There we go. Lost it. For the Suzuki reaction, you couple an sp2 hybridized carbon on an aryl or vinyl halide with the sp2 hybridized carbon on an aryl or vinyl boronic ester. So it's all about here's the new sigma bond you make. You have sp2 hybridized carbons on either side, and yeah, you've got aryl or vinyl here, aryl or vinyl here. If you go to the, and this has to be a halide and this has to be a boronic acid or a boronic ester. If you go to the Heck reaction, the substrate scope is similar, but a little bit different. On the one hand, you have an aryl or vinyl halide, so same substrate scope with one partner, but over here, there's no boronic ester. In fact, there's no real requirement for specific functional groups at all. It tends to be just an olefin carbon with an electron withdrawing group. So a little bit broader substrate scope with the Heck reaction. You don't need to go to the trouble of making the boronic ester. They're similar enough that Heck and Suzuki and some others shared the Nobel Prize, though, for this kind of cross-coupling reaction. Good, others? Yeah.
But both of them create the same end product.
No, well, yes, you could imagine making similar products through the reaction. If I had replaced one of these hydrogens with the boronic ester, that would have been a Suzuki reaction. So the Heck reaction, like the Suzuki, does make sigma bonds between an aryl or vinyl sp2 hybridized carbon, and then on this side just a vinyl sp2 hybridized carbon. So it's a little bit more limited. In the Suzuki reaction, you can make aryl bonds, but presumably not with the Heck reaction. So it's a little bit, Suzuki maybe is a little bit more versatile. Others? Yeah.
For the Heck reaction, the very last step with reductive elimination, could reductive elimination have occurred with just binding the hydrogen and iodine, and then having that leave, and then having, oh, actually, no, I think that's what happened.
Yeah, what I showed, the mechanism I showed was reductive elimination first to make HI, and then a base removes the proton from HI. And I don't actually know this, but you could make a reasonable mechanism as well, where a base would deprotonate the metal, and then iodide would leave as a leaving group. And I'm not actually sure and I'm showing you a mechanism that I think is a little bit more detailed than what is presented in the text. But yeah, I don't actually know about that. It's a good question. Others? Yeah.
Can you explain how to understand the stereochemistry of cyclopropane?
Sure. So the Simmons-Smith cyclopropanation should look a little bit similar to you as, well, or rather the cyclopropanation reactions with carbines in general are stereospecific. It should sort of in your mind resemble what we did with epoxide formation. That is, the stereochemistry of the alkene in the starting material affects the stereochemistry of the epoxide form. Do you remember that from 351, how if you started with a trans alkene, the methyl groups that were trans in the alkene would still be trans in the epoxide? It's the exact same thing here. Yeah, because the reaction is concerted. Two things happening at once. The alkene electrons attack the empty p orbital on the carbene, and then the sp2 electrons on the carbene attack the other carbon of the alkene. Those two bonds happen. It's a syn addition. They happen from the same side of the double bond, and so the stereochemistry is preserved, which is why if you start with the trans, you get the trans cyclopropane. If you start with the cis alkene, you get the cis cyclopropane.
Okay.
Is that what you're thinking?
Yeah.
Yeah, good. Go ahead.
After the ligand binding step in a Heck reaction, why is one of the vinyls L and the other vinyl is X?
Okay, so good question. Zooming in here, this is the ligand binding step of the Heck reaction. I'm really sorry about the glare. Just sort of do our best. Prior to the ligand binding step, you have the vinyl ligand, which is formed by oxidative addition of the vinyl halide to the palladium. So one pair of electrons in these palladium carbon and palladium metal bonds comes from the carbon iodide bond. The other pair of electrons comes from palladium. You can't really tell which is which, but I'll just label them in different colors so you know that they have different sources. That's why we go from palladium 0 to palladium 2. And that's now an X ligand, because if it left with its electrons, it would be negatively charged. Based on the fact that these are two X ligands versus L-type ligands, you can conclude that this is palladium 2, that there are 8 D electrons, and that this complex has 16 electrons total. That means there's room for this ligand to bind. This is also a vinyl group, but notice, and I didn't draw in the hydrogens that are implied but not shown, this ligand is neutral. So when it binds to the metal, because it's neutral, it's an L-type ligand. What's binding to the metal is the pi electrons, and I've tried to show that by having a dotted line from the pi electrons to the palladium. So whether something's L-type or X-type all depends on when it leaves, is it neutral or negatively charged? So because we can fill in the hydrogens that are missing on the other vinyl ligand, we've got a direct carbon palladium sigma bond there. If this group left with the electrons, it would be negatively charged. If this group left, it would be neutral. You see that? Yeah? Okay? Yeah?
Is there anything that keeps the other ligands from interacting with each other and making the wrong types of bonds that you don't want?
It's a good question. What keeps the other ligands from interacting with each other and making the wrong kinds of bonds? I don't know that I have a great answer to that. In fact, I'm pretty sure I don't. I think one thing that helps here in the Heck reaction is at the end you have a reductive elimination step that generates HI, which is immediately deprotonated by the base. And I think that pulls the reaction forward in this direction. The phosphine ligands really don't do reductive elimination. If they did, you'd have a phosphorus-phosphorus bond, which isn't really that stable. So I think there's some thermodynamic issues that help the reaction proceed. And these are really issues that people have worked out. Often reactions are discovered, and then people have to try to tease out what the mechanism is through some really detailed, what are called kinetic experiments. So just like we understood the mechanism of the SN2 reaction because the alkyl halide and the nucleophile were both in the rate law, so you can tease out the mechanism here by changing concentrations of starting materials and see how the rate is influenced. And there are some other more sophisticated sort of kinetic experiments you can do to try to determine what the mechanism is. Yeah. I just don't know what they are. And the other thing you do is you do computations to measure the energies of various intermediates and transition states that lead to those intermediates, and you try to find the lowest energy pathway, and that's usually the one that's operative. Okay, good. Others? Sure.
In the textbook, sometimes it talks about how you can't necessarily create
Okay.
Are there any other limitations
Sure.
there?
Well, the idea there, let's see where we go. Making organoboranes. One strategy is hydroboration of alkynes. That's a 351 reaction. That because hydroboration is a syn addition of boron and hydrogen, you're sort of limited in stereochemistry. The boron is always going to be trans to the R group. Your text doesn't really solve the problem. What if you want the Z vinyl borane? Though I think that's a solved problem. Your text just doesn't present it. You're not responsible for it. In terms of another strategy, that's to go through an organolithium reagent which you react with trimethylborate. And the idea here is all of the same limitations of organolithium reagents here apply. So do you remember protecting groups and trying to avoid protic solvents with organolithium reagents? Anything that could be deprotonated by this is likely to interfere with the reaction. So that's all that's going on there. Nothing really new. Okay, what else? All right, so in some ways, the reaction is simple because it's sort of it's a simple coupling reaction. As long as you can identify this is a Suzuki reaction based on the substrates and the reagents, then it's pretty easy. You just click the two carbons together with a sigma bond in terms of predicting the products. The challenge is going to be these are unfamiliar and you may not recognize them. So we've not used organoboranes for any other purpose. So you're going to need to recognize that as a substrate for a Suzuki reaction. Another potential confusion point is that Suzuki and Heck both start with aryl or vinyl bromides, and both of them involve palladium. So you're going to have to memorize or find a way to remember the different catalyst that's used for Suzuki versus Heck. Suzuki uses a palladium 0 catalyst, and this is a major difference with the Heck reaction. The Heck reaction uses not palladium 0, but palladium 2. That's bizarre because the active catalyst in the Heck reaction is actually palladium 0. But so why they start with palladium 2, I'm not sure. There's likely an explanation for that, I just don't know it. So you'll have to recognize the Heck reaction conditions versus the Suzuki reaction conditions, the Heck starting materials versus the Suzuki starting materials. Okay, yeah.
For the Suzuki reaction, will you ever get a cis product, or is it always going to be trans? Because I know that Heck is selected for trans, like you were expecting.
The Suzuki reaction stereochemistry is the stereochemistry, the starting materials are preserved in the product. Notice that in the Suzuki reaction, you're only making a sigma bond. So if your organoborane has E stereochemistry, that portion is still going to be E over here. Okay. And same thing with the aryl, or sorry, if this were a vinyl halide, I don't know if I have an example of that, but you certainly did some, I think, in practice problems. Whatever the stereochemistry of the aryl, or rather the vinyl halide is, that's going to be preserved in the product too. Yes, so there's an example of that. A vinyl iodide where the I is trans to this ethyl group, and then a vinyl organoborane where the boron is trans to this ethyl group. Both of those remain unchanged. Just a second, I'm going to point out, by the way, that this is a diene. And you guys know stuff you can do with dienes. We learned about the Diels-Alder reaction, or you did in 351. That can be a nice way to build on a synthesis question, to think, okay, first I got to make the diene, and then I got to do a Diels-Alder reaction. You asked about stereochemistry with the Heck reaction. The Heck reaction is interesting because of this, the stereochemistry of the vinyl iodide or the aryl iodide stays the same. There isn't any stereochemistry about this olefin because it's a terminal olefin. There's no E or Z. But when we do the migratory insertion step, the double bond goes away, and then we reestablish the double bond via beta hydride elimination. So that we sort of take the double bond away, then we put it back, and that's the step that is selective for trans. Yeah, so for the Heck reaction, you expect in the product to get trans here. It's not that the stereochemistry of the starting material is preserved, because there is no stereochemistry there, but we put the new carbon-carbon bond in place such that we get the trans relationship between these groups. Okay, back to you. You had a question?
What's the function of the p-toluene, and do we see that in the mechanism at all?
This is a ligand. So this is a phosphine, the p-ortho-tolulyl ligand. Let's see if I can get to it. Looks like this. That's just like PPH3, triphenylphosphine, only there's 3 additional methyl groups at the ortho position. There are a huge number of potential phosphine ligands, and this happens to be the one that your text chooses. There are other choices you could make. Whenever you invent a reaction like this, people often screen or test a large number of phosphine ligands, and they choose the one that works best. And there's often reasons for why one phosphine ligand works better than others. That's not explored in your text or explained in any detail. Mechanistically, what's going on is I just didn't want to write out O-tolulyl there, so the R3 or those ortho-toluene groups. Okay, others, yeah.
And then, so going back to what you're talking about, the Suzuki reaction, the organoporane, if instead it was cis rather than trans, it
Yes.
would show that in the end product.
That's right. That's right. Whatever the stereochemistry of the organoborane is present in the end product. So if it were cis rather than trans, it would also be Z over here. Good. Okay. Others? Yeah.
Maybe this is mostly just a review question, but are there any limitations on the conversion of, for example, an aryl halide to an organolithium? I'm assuming it's not an SN2 reaction.
No, and that's a reaction that we glossed over earlier on in organolithium reagents. We didn't talk about the mechanism of lithium metal replacing the boron. It's Br minus is the so-called leaving group, but it's not an SN2 reaction. It actually involves single electron transfer from a couple of metals, probably to the, well, anyway. So that's probably a memorized reaction because we didn't talk about the mechanism of it.
It's not even a concern when it's a vinyl halide or aryl halide, it just works.
No, we've done that a ton, yeah. So you could do this with any alkyl halide. The only problem is for the Suzuki reaction, you want it to be aryl or vinyl. Yeah. Okay. Well, okay, yeah.
Sorry, one more. Could you really quickly show the conversion of the POAC2 to the first step of the Heck reaction in the mechanism?
Did I not do that? I probably didn't want to. Okay, here it is. This is not in your text. It's not something to worry about, but I often get irritated by these kinds of details, so I just wanted to show you what likely is going on. This is the palladium acetate starting material, and it's palladium 2. These acetate ligands, if they left, would leave as the conjugate base of acetic acid, or OAC minus. So each of these, it's a bidentate ligand. It binds to palladium at 2 sites, but overall they are X-type ligands because if they leave, they're negatively charged. The complex is neutral. That means it's palladium 2. It's a D8 complex with 16 electrons overall. There's ligand exchange or ligand binding where the 2 acetate ligands leave, and then anywhere from 3 or 4 phosphine ligands could bind the palladium. I guess these should be PR3 because it's the toluene ligands. Then it's thought we need to somehow reduce this complex from palladium 2 to palladium 0. It's thought that the way that happens is one of the acetate ligands binds the palladium. The overall complex at this stage is +2 because the 2 acetates have left and the phosphine ligands are neutral. So this is a ligand exchange reaction. Once the oxygen binds the palladium, if you do a reductive elimination step where you would make a new sigma bond between oxygen and phosphorus, that reduces you to palladium 0. And oxygen phosphorus bonds are actually pretty strong. And and there's some other things that happen to this, but it's thought that the formation of the oxygen phosphorus bond drives this reductive elimination step. So they think that's what's going on. As I said, that's not necessarily important for you to worry about, but it's something that made me uncomfortable, so I looked it up and I put it there in case you wanted to know. Okay, well, there's one more reaction we need to introduce in this chapter, and that's it's one that involves a different metal besides palladium. The mechanism is complicated, but it doesn't involve any change in oxidation state. So there's not going to be any oxidative addition or reductive elimination. But the reaction is called olefin metathesis. So that's going to be our final reaction in chapter 28. And this is also a Nobel Prize winning reaction. It involves a ruthenium catalyst, and there are various versions of this, but the most famous is one that was developed by Professor Bob Grubbs at Caltech, who died a couple of years ago, but won the Nobel Prize for this at some point in the 2000s. So I'll show you what this catalyst looks like. It has phosphine ligands. It's ruthenium rather than palladium. So look at the periodic table. Ruthenium is 1 row down from iron. We could do oxidation state with ruthenium here, and maybe we will. But as I said, there's not any changes of oxidation state in this reaction. There's this unusual ligand. This is, I suppose you could call it an X-type ligand. It's called an alkylidine. If it left, it would leave as that, which would have, let's see, 1, 2, 3, 4, 5, 6. So that would be carbon 2 minus. So it's sort of an X-type ligand, but it's doubly negatively charged. But you can think of this as having both carbon, ruthenium, sigma, and pi bonds. So this is a metal alkylidine. In addition to that basic structure, you've got 2 chloroligands. So those are also X-type ligands. And then you have two L-type ligands. These are phosphine ligands, only the things attached to the phosphorus are not going to be phenyl groups or toluene groups. They're going to be now just cyclohexyl groups. Why cyclohexyl instead of phenyl? My guess is the Grubbs lab tried them and the cyclohexyl worked better. Sometimes having steric bulk in the ligands can change the course of a reaction or accelerate it. So this is called the Grubbs catalyst. And there are multiple variations on this. Some are called Grubbs Generation 1, some are called Grubbs Generation 2. We're not going to worry about that. We could look at this complex though and assign its oxidation state. The palladiums are both L-type ligands, and the two chloros and the alkylidine are X-type ligands. The complex is neutral, so that would allow us to go through and sort of figure out where we are with ruthenium. Though your text doesn't go through, and I'm a little bit uncomfortable with the alkylidine ligand, and I'm not sure I've described it correctly. So I'm not going to ask you to assign d-electron count or oxidation state for the ruthenium ion, just because I'm afraid I'm going to get it wrong. All right. So with that in mind, let's just show you how we'll abbreviate the Grubbs catalyst because, well, we're going to abbreviate the cyclohexane substituent because it's a pain to draw. We're just going to call that CY. So you'll see that phosphine ligand as PCY3. All right, so that's the catalyst. Now let me show you the reaction, just in a predict the product sense. So I'm going to take these two terminal alkenes, and we're going to use the Grubbs catalyst, which is ruthenium, the alkylidine ligand, the two chloro groups, and then the phosphine ligands. And this reaction takes the two vinyl carbons, the two internal vinyl carbons, and bonds them together. And you would get both cis and trans isomers, and the ratio of them should be the ratio of the two of them should be basically weighted according to their different stabilities. And then the other thing you get is the two terminal carbons from your olefins now bonded together. So the two pink carbons get bonded together, and then the blue and the orange carbons get bonded together. I like to think of this reaction as sort of Lego building reaction where you take two pieces, you pop them apart, you take two other pieces, you pop them apart, and then you mix and match. And that's really the meaning of the reaction name metathesis. That's basically breaking the carbon-carbon and sigma and pi bonds, putting the orange and the blue carbons together, and then putting the pink carbons together. The metathesis reaction is an equilibrium reaction, and so you have to choose your starting materials carefully such that the reaction can go to completion. The thing that drives the reaction I've just shown you to completion is that one of the products is ethylene, which is a gas and bubbles off and removes itself from the equilibrium, thereby driving the reaction forward. You can make this reaction a huge mess if you don't choose carefully. For example, suppose I chose, I'm going to make this as terrible as it can be. How's that? No one in their right mind would ever, in a gazillion years, do this reaction. We're going to need color to help us along. Let's see, I'm trying to avoid green, but there we go. Running out of options. If you don't have one partner that will remove itself from the equilibrium, and you attempt to do metathesis on this kind of these two starting materials, these two alkenes, you're going to get all the possible products. And they're going to be in equilibrium with the starting materials. So that means I expect a product where the blue carbons are bonded together, and I also expect to get the cis version of that. I think, I'm trying to figure out, but I think in the end we're going to have like 16 different products here. Not that you should be prepared to deal with that, but what I'm trying to explain to you is that not all versions of metathesis are useful, and so you have to be careful about it. Oh my gosh, we're going to have like way more than 16, aren't we? All possible combinations. Should we just do it? It's just time. We got all the time in the world. So you have all of these self-metathesis products. I'm really sort of wishing I didn't do this, but what's going on with these products is the catalyst is breaking the bond between the blue and the pink carbons in multiple molecules, and then two blue are getting stitched together, and two pink are getting stitched together, or two orange are getting stitched together, or two green are getting stitched together. Okay, so you'd have all of those sort of self-metathesis products. Then you would have all the possible combinations of blue and orange, blue and green, pink and orange, pink and green. Let's see, that's blue and orange, right? Then let's do blue and green. And let's see, there would be pink and orange. And then pink and green. What a mess. And because I'm tired, I'm going to continue to draw the cis. Let's see, did I miss any other options? Yeah.
Did you also have the cis forms of the starting materials?
Yep, you're gonna also get the cis forms of the starting materials. Since they're not starting materials, I'm gonna move them over here. But yeah, you're gonna recover that and perhaps some of the cis. And again, the relative amount of cis versus trans is gonna depend on stability. So the message to take home is the metathesis reaction's really cool in that it pops two doubly bonded carbons apart and mixes and matches them. But the problem with that is that you're going to mix and match them in all possible combinations unless there is a strong thermodynamic driving force for the reaction to go a certain way. So this is an example of a reaction where the catalyst is really powerful, but you have to be smart about how you choose your starting materials to avoid this mess. Oh, that is, look at all of the things we've had to do to get Jack on his mission. I don't want notifications. I don't know why I clicked on that. No, please do not install. Gosh. All right, so something on the order of 16 different products, all sort of possible combinations. I know that strikes fear into your heart because you're anticipating a predict products question where you have to get all 16. On the other hand, there's only like 10 options, so I wouldn't worry about that. Yeah?
For the top one,
Yeah.
why don't we get self-metathesis with like blue, pink, finding another one, or like yellow, pink, finding another?
Okay, excellent. Yeah, so why don't we get, for the top one, why don't we get blue finding blue and orange finding orange? I think you would. And so I should have drawn that as a potential problem of blue finding blue, orange finding orange, and their cis options. Only slightly less messy. These two are examples of what we're going to call cross-metathesis products. And these are examples of self-metathesis products. And all of them, we're not going to get any, the reason that pink isn't involved is because pink is going to remove itself from the equilibrium by making ethylene and bubbling out. Yeah. So, okay, under what conditions then is metathesis really useful? And as I said, you're going to take advantage of starting material or substrate so that you remove some players from the equilibrium. The other thing you can do to prevent, 6 is still way better than 16, but to prevent this sort of competition between self and cross-metathesis products, the other thing you can do is to make it intramolecular. And that tends to speed the reaction up and move it in a particular direction, because intramolecular reactions are fast. So intramolecular metathesis reaction would look like this. So let's imagine the following alkene. And then let's use that ruthenium catalyst. Look for the terminal alkene. Look for the terminal CH2 group. That's going to come off as ethylene. These are the sigma and pi bonds that you're going to break. One of your products is going to be ethylene. And then the other two carbons are going to be linked together here and here. They're going to be linked together through a sigma and pi bond, and then you just need to count carbons to figure out what size ring it's going to be, and that's 6. So here is a 6-membered ring. 1, 2, 3, 4, 5, and 6. And that product, that intramolecular product, is favored over the potential intermolecular option. So some of you may be thinking, well, what about this? Could I get 1, 2, 3, 4, 5, 6? This kind of a polymer where blue is attached to blue and orange is attached to orange and so on. That's a possibility, but the intermolecular product is slower to form than the intramolecular product. And that'll become clearer when we look at the mechanism. So this is another case where you can control and get the cross metathesis product because the intramolecular reaction is faster. Does that make sense a little bit? So this is called, another term for this instead of intramolecular metathesis, this is called ring closing metathesis. And this has been used all over the place. Yeah.
When we work so hard to form carbon-carbon bonds, why would we use this reaction that gets rid of carbon-carbon bonds?
When we work so hard to form carbon-carbon bonds, why would we use this that gets rid of it? It's a good question. I mean, we're losing basically a sigma and a pi. From a strictly counting number of bonds point of view, we don't lose any bonds. We just trade what their partners are. Sigma and pi here, sigma and pi there, sigma and pi here, sigma and pi there. Now, I agree with you synthetically, if we were going to move forward, likely we're not planning on doing anything with ethylene, though I suppose if we wanted to, we could capture it and then do stuff with it. So it's something of a loss there. Some synthetic chemists would criticize this reaction as not being what is called atom economical because you're losing stuff that you don't intend to do anything with. That's a criticism of a lot of organic chemistry reactions, though. But from a thermodynamic point of view, we're not losing any bonds. We have the same kind of bonds, same number and same kind of bonds in starting materials versus products. Okay, others? So I do want to show you the mechanism of the reaction to give you a sense for why the intramolecular reaction is faster. And then I'll show you some applications of the reaction in research and stuff. All right. But we're at a decent stopping point, so let's take 5. And then we'll dive back in.